All right, here's 3-5. A really big shift from 3-3 and 3-4, right? Where it was zeros and synthetic division and polynomials and, using zeros to find the function, or the function is given to you and find the zeros. Big shift. All word problems. It's normal today if you look at what you're seeing and be like, all right, we're dealing with functions and we have a couple different types, but not everything is reminding me of polynomials. And that's going to be true. Okay, I think there's one in here where I use a quadratic. It's not, this is kind of the appropriate spot for this lesson because it's kind of the best spot for it to go. But as far as like the applications here are, like, modeling is taking data and writing an equation. Okay, that's not really going to be something that we get into for third-degree polynomials or higher. Most of the ones you're seeing today are linear, possibly a quadratic. One of them is a quadratic. There's a couple you wouldn't even recognize that are actually rational. Because again, that's a function type that I don't believe we've still really taken that on altogether, and I think we've seen them some, not a ton, right? But you wouldn't have to know it to solve them, okay? So to write an equation, this is a direct variation model. What that means is as x goes up, y goes up, okay? Basically goes like this. You need to plug in x and y and solve for k, right? Now don't get fooled with different problems and their context, right? They may not call the variables x and y, right? If t is temperature, they might call it t. If p is pressure, they might call it p. If it's distance, right? They may call that variable d, but keep track of x and y, okay? And then really this value of k, it's kind of like this missing piece, that is what you're looking for, okay? Define k. Now, one thing you typically need to do if the problem doesn't do it for you is if you're writing an equation, you have to define variables, okay? So for example, right here, I need to right off the bat say that x is gross income. And it really is a good process to go through anyway, even if you aren't thrilled that you have to write these out, which is like on a test you do need to write them out. Gross income in dollars, and then y is going to be state income tax. And that is also going to be measured in dollars, okay? But one of the key things when you're doing modeling, again, using data to write an equation, is you need to keep track of your variables. So even if you weren't writing this out, it's what you should be thinking about to get the problem started. If you can't get it kind of straight in your head that, x is going to be income, so you put your income into this function and the y value tells you, here's what you owe for your state income tax, okay? So I'll head over here, get started. It's a direct variation model. As x goes up, y goes up. So here's what step 2 is saying. We have a piece of data that says if you made $1,500, as your gross income, your state income tax that you owe is $46.05. You'll see a theme on all these today, other than the last one, which is a little bit trickier because it has 2 types of variation on it. The steps to solve are not extremely long. They're not extremely long. Probably need a calculator to help me out with 46.05 divided by 1,500. And then to write my final answer, y equals 0.0307 times x. And there you go. Okay? That, again, is what we mean by writing a model. I now have this function with the variables defined that tells me you give me gross income, I can tell you the state income tax that would be owed off of that income. All right, here's the one that's a quadratic. Okay, it's the same idea. It's a direct variation model, but you see in part 3 that you may have, kind of depending on your data, your x variable may not be raised to the first power. In our previous problem, the one that we just did on the state income, it was. But you may have others that aren't like that. Okay, ball rolls down an inclined plane, directly proportional, right? Which again, when you see that, think x goes up, y goes up, to the square of the time it rolls. Okay, so here's basically what is going on. My general form is going to be like this. Y equals kx squared. Okay, and I'm going to stick with x and y just because, but I could easily have changed the names here. X is time. That is going to be measured in seconds. Y is distance. And I believe we're going to measure that in feet. Let me double check. Yes, y is being measured in feet. All right, so once we have that set up, we really take the same approach that we need a value for x and y to plug in, which we have. It says during the first second, the ball rolls 8 feet. Perfect. When y is 8, x is 1. Again, pretty minimal solving to get k, not too bad. Which leaves us with this, y equals 8x squared, a very basic quadratic, right? Just has one term. There's no, in the value for a, even though in this case we're calling it k, but if we thought of it as the coefficient in front of x squared, that's 8. There's no x term and there's no constant term, right? So it's a pretty simple little quadratic. Next question is, how far is the ball rolled after 3 seconds? Well, once I have my function, there's a lot of questions I could answer about this situation. Plug in 3 for x squared, I get 9 times 8, 72 feet, right? Now, just kind of on the context of that problem, like that ball rolling down the inclined plane, this is obviously kind of a physics type of problem. That model had to be quadratic. It's largely because gravity is what's pulling it down, and gravity tends to follow quadratic principles in its motion. But we couldn't do it like the other one, because if x was raised to the first power, then it would mean that every second the ball rolls 8 feet. That's not the case, right? It rolled 8 seconds or 8 feet in the first second, but then as this ball goes down this inclined plane, it starts to roll faster and faster. So it covered more distance in the second, and then it covered even more in the third. That's why we need the x squared, right? A first power or a linear model would not have been appropriate. All right, here's an inverse proportional, right? Notice the different structure to the equation. Big idea here, x goes up, y goes down. All right, so I'm looking through my context here. My x variable is going to be price. I'm going to measure that in dollars. Notice when I define the variable, I do like to include the units. Y is the demand. Units are just like how many they expect to sell, right? So obviously switching context here from quite a bit, from a physics example to one that's really an economics example, but it's worth kind of just addressing the context to see why are we switching to an inverse model. As price goes up, the demand goes down. In other words, the product that they're selling, which it does not say what it is, which for our purposes to write the equation, it doesn't matter what it is that they're selling. If they make it more expensive, they're going to sell fewer of them, right? They make it more expensive, they're going to sell fewer of them, okay? If they make it cheaper, they're going to sell more. Okay. We do have a point, right? They have evidence that if they price the item at $6.25, they're going to sell 400. The demand will be 400. Again, K is not too bad to solve for. Multiply both sides by 6.25. And there's kind of the missing piece to our model, that K is 2,500, which would lead me right back up here. That for any other situation I want to look about supply and demand for this, I shouldn't say supply and demand, for price and demand for this product, I can use that function, y equals 2,500 over x. Because it does ask us a follow-up question, what would we expect to sell in terms of units? What would the demand be? If instead of pricing it at 625, what if we priced it at 575? Now, before you punch that into a calculator, I think it's good to kind of to think it through to make sure you've got a good expectation to kind of test and see that your answer is correct. Right? They're putting the price lower, and this is inversely proportional, right? So that tells us if they drop the price, the demand should go up. And it does, right? 2,000 divided by 575. We got to do a little bit of rounding. Whoops. Dollars. And this is a Y variable. Units aren't dollars. Units are units. And it does. They would sell a few more of them. 435 units is what they would expect to sell. All right, so we've seen two direct, one inverse, okay? Now, about the only wrinkle that I've given you is that second one had a variable that was squared. These last two examples that we'll look at both have a little wrinkle to it as well, okay? This one's called joint variation. Okay, which means basically we've got multiple variables. Okay, and all these we've just had two. Okay, we've just had two. That's not going to be the case on this one. Okay, it's a formula for simple interest, right? So we're going to use it to calculate interest. But simple interest is a product of three things: the rate, the principal, and time. Okay, now I really should define all these. Interest is how much money that the investment earns. Okay? Instead of really being a function of one thing, it's a function of three things, okay? One of which is your rate, which that's really going to be the focus. You could actually think of this in this problem. R is like K. It's kind of the missing piece that we need. P is principal. It's how much money you put into the investment, okay? That one's a little more straightforward, as it tells you right there that you put $5,000 into this investment, okay? And T is time. If you're doing simple interest, it's almost always measured in years, okay? So again, that's the difference on this problem is there's more, like, I had to define four things, right? Because like on the other one with the demand and the price, there was one thing that we were saying is going to affect the demand for the product. Okay, remember I'm jumping back to the previous example, and that was the price. Okay, as the price went up, the demand went down. Here there's three things that would affect how much interest we earn. What's our interest rate? How much principal did we invest? And how much time did we put the investment, how much time did it have to earn money? So we need the rate. That's the big piece that's missing, because the information that we're told. Right, so now if I think of R like K, by the way, that means I need all three of these. I need to know how much money was invested, for how long, and how much did it earn, which it gives us. It earned $43.75. We don't know the rate. $5,000 was invested, and this part gets a little bit tricky. Time has to be in years. It was invested for 3 months, so that's 1/4 of a year. Okay? I'm going to go ahead and solve this. This would be R times 1250. And I'll take 43.75 over 1250, which is 0.035. That's the big missing piece to our whole simple interest situation, that we now know the investment is earning 3.5% per year. Okay. Follow-up question. All right, in this situation, because that's really where it leaves us now. Is it's like, all right, interest is 0.035. We'll assume that they stay with the same principal invested of $5,000. And now it's kind of like we have two variables. You just need to know, okay, so if you invested $5,000 at 3.5%, now the interest really just depends on how long are you going to let the investment go. It wants to know, what are we going to earn if we let it go for 15 years? So T would just have to be 15. You throw that whole right side into a calculator. $2,625 is the amount that the investment would earn over that time, given all that information. All right, last one. Right, this one also has a little bit of a wrinkle on it. Right, like the last one was all. I didn't really emphasize it, but the simple interest problem was all direct variation. Right. If the interest rate went up, the amount of interest you earned went up. If the principal went up, interest went up. If time went up, interest went up. Okay, so that whole, it had multiple variables that they were all direct. Okay. So combined variation. Here's the deal on this one. It combines direct and inverse. Okay. Direct and inverse. So here's what you're looking at. For what it's describing in the context is it says that we're looking basically for an equation for volume, the amount of volume a gas takes up. But it depends on two things: the temperature, and it's directly related to the temperature. In other words, the more you heat a gas up, the more space it takes. It expands as it heats and takes up more volume. Okay? The other piece is the pressure that's applied to it. That would be inverse. If you apply pressure to it, the volume will go down. we've got volume. I believe in this problem it is in cubic centimeters. T is temperature. In the old Kelvin scale, you got to be in pretty science-related stuff to be using Kelvin. Pressure looks to be kilograms per centimeter squared. And I mean, those seem like they could be relatively confusing units. We don't really need to get into them, right, to do the math. Like, maybe I'll slap those units on my answer, but that's about all I'd have to do. All right, so to do this, we need some information, which, of course, we have. It says if the volume is 8,000, right, because we're after K, but it takes up 8,000 cubic centimeters when the temperature is 294 and the pressure is 0.75. Okay? I'd multiply both sides by 0.75 and get 6,000 equals K times 294. Divide by 294 and get that, which is really the answer that I'm looking for. However, I'm going to do some simplifying here. Both of those numbers are divisible by 6. I am going to leave an exact answer, but I just reduced it. Biggest factor they had in common was 6. So now, volume, I found K. By the way, if you were to divide that out, it's like a little bit over 20 is what K is. All right, there's your function. Volume is 1,000 over 94 times temperature over pressure, okay? And again, we've got those two variables on the right side, one of which the volume is directly related to, the other it's inversely related to. So now let's head down to the bottom and, use it a little bit. Find the pressure when the temperature is 300. And the volume is 7,000, right? So yeah, I've got 3 things missing. If I want to solve for one, I need 2. So it tells me 7,000 and we're looking for pressure. So that's the equation we would have to solve, right? First thing I would do is multiply both sides by P. So then get pressure times 7,000 equals, right, if I multiply 1,000 by 300, that's coming from the line above, I would get that. And then really I just have to divide by 7,000. Obviously I'm going to be headed towards my calculator here pretty soon. If you were to throw that in your calculator, be really careful that 3,000 over 49, switch it to a decimal first or make sure to put it in parentheses. Otherwise, your answer will be a mess, okay? Yeah, just be safe. Anytime you're using a fraction like that, when you put in your calculator, put parentheses around it, okay? Here we'll go with the decimal as our answer. 0.87, and for pressure it was kilograms per centimeter squared. And there you have it. All right, that's all for 3.5. And as a matter of fact, in terms of lessons, that's all for Chapter 3. Good work.